Hi everyone. Thank you so much for having me. I will be presenting joint work, learn uniform circuit lower bounds and provability in bounded arithmetic. Luckily, Yan has already told you all about bounded arithmetic, and I encourage you to direct questions to him and Sasha instead of me about it. This is joint work with Valentin Kabinets, Antonina Kolokolova, and Igor Oliveria. This appeared in Fox this year, or I guess like last year technically. Fox 2021, which happened in 2022. All right, let's get started. So we want to know how difficult it is to solve our problems, like our decision problems, our computational problems. And at the same time, we also want to know how difficult it is to prove our theorems. And one of these is called computational complexity. The other is called proof complexity. And this room is full of people who do both. So of course we can jam these questions together and then ask ourselves, how difficult is it to prove theorems about computational complexity? That's the only question that I have a really good general answer for. It's very hard, and my source for that is personal painful experience. So it's this middle question that we'll be talking about today, and that we cover in our paper, is really the meta-mathematics of computational complexity. Exactly how difficult is it? What kinds of proof theoretic resources do you need to use to prove the theorems that we care about, to answer our questions? Okay, so let's start with some questions about complexity theory. Here's P versus NP, but for circuits, right? Does SAT have polynomially sized non-uniform Boolean circuits? And again, it's a luxury to come in at the end of this workshop. I think like 8 people have defined circuits and SAT before me. So we all care about this question. And we generally conjecture that SAT doesn't have poly-sized circuits. We conjecture the non-uniform version of P versus NP. And here's a meta question about that conjecture. If we're wrong, right? Like let's suppose we're super wrong about that. How hard is it to refute? What kinds of proof theoretic resources would we need to marshal to prove that poly-sized circuits for SAT do indeed exist? But we can't answer those questions today in our talk. If we could, that would be amazing. Like even answering that meta-mathematical question about comp sci would be awesome. So let's go to some easier questions, right? And how are we going to make these questions easier? We're going to make the question way more aggressive, right? We're going to say, okay, so like we don't know about SAT having poly-sized circuits. Does all of NP have quadratic-sized circuits? I don't know. We still don't know. I think even this has appeared on a bunch of slides before my talk, right? It's possible. Here's the lower bound conjecture, that there just exists some language in NP where, again, I'm allowing you to use an arbitrary polynomial, fixed polynomial amount of non-deterministic time, and you just have to prove to me that it doesn't have quadratic-sized non-uniform circuits. So we conjecture this is true, generally. And here's the meta question again, right? Let's say we're wrong about even this. What kinds of reasoning would we have to marshal to refute this conjecture? What kind of proof system would suffice to prove that these circuits exist? And we can actually formally answer this meta question. That's what's in our paper, and a beautiful line of work going back to Cook and Kryzak in 2007, where they study the provability of questions like this. What does that answer look like? Essentially, we say that there's a natural theory, T, which is a way of formalizing reasoning that I will claim that it is formal and then not formalize it at all today because it's the last talk of the workshop. And this theory is natural in the sense that it's powerful and interesting. Like it proves results that we care about. Due to Yam-Pick, it proves the PCP theorem, which is a pretty beefy theorem. Like that's an entire semester of a graduate level class in complexity theory sometimes. So it's a strong theory, but it unconditionally does not prove that NP has quadratic sized circuits, okay? So what is this result saying? It's saying kind of like one of two things. It's saying, all right, let's say you believe NP, all of it, has quadratic sized circuits. You can't prove that in PV. It's giving you useful information. You have to escape PV and use mathematical techniques outside of it to prove that NP has quadratic sized circuits. Or it's telling people who believe the lower bound conjecture that, oh, here's this theory that proves a lot of stuff that we care about, that's powerful and rich. From the point of view of this theory, the lower bound is true. It's consistent with the theory. So in this sense, it's progress towards proving these kinds of lower bounds to show that they are consistent with increasingly strong and interesting theories. So there's something here for both sides of the equation, for whether you believe in like super crazy circuit upper bounds or whether you believe in circuit lower bounds. You get some useful guidance for the future. All right, so I'm going to say a very little bit about what a natural theory is. So in complexity theory, we have decision problems like SAT and graph reachability, right? And we measure their computational complexity with stuff like the runtime of an algorithm or the size of a circuit. However, in the task of proving theorems, we have target theorems, like this algorithm is correct, or a circuit exists to solve this problem. And notice how those are fundamentally different, right? Because when you're talking about the existence of circuits, you're talking about the existence of an infinite sequence of objects, each of which has like a nice fixed size. When you're talking about correctness of algorithms, you're talking about behavior of inputs on one fixed algorithm, but you can formalize both of them appropriately. The way that we measure this is proof complexity. Coming from like a very track A theory, I don't know much about this at all. So let me tell you very briefly what I mean by proof complexity. It's going to mean bounded arithmetic. It means we start with a set of axioms. They're a subsystem of PA. They describe some basic properties. They're actually called basic in Sam Buss's beautiful thesis that introduces this, of numbers and strings. Then we have some inference rules. That corresponds to the Frege systems that Yen was talking about just earlier. And we apply the inference rules to the axioms. We take the closure of that, and all of those derivable theorems, we call that a theory. Great. For the purposes of this talk, that is my super informal account of all of bounded arithmetic. Now, what's a natural theory? From the point of view of computation, from the point of view of somebody who's kind of raised in the first chunk of this diagram. Well, I'm very lazy. I would like it if all of these theories corresponded in like a perfect, like one-to-one way with uniform complexity classes. So I can just think to myself, okay, if I'm dealing with this theory over here, it's basically about as smart as log space. Or like this theory is about as smart as BPP, or polynomial time. And that seems like actually kind of a big ask, right? Like, should there be such a beautiful connection between, you know, computational complexity and like very precise subsystems of Peano arithmetic? Turns out there totally is. It's great. It's called bounded arithmetic. This is the advertisement section of this talk. These are very natural theories where you can write statements in logic that basically look like you're being super, super careful in your Aurora Barak homework, right? But actually it's a whole formal theory, and they're derived from complexity classes. So for example, VPV is derived from deterministic polynomial time, and it proves the PCP theorem. VAPC1 is derived from randomized polynomial time, and it proves that bipartite perfect matching is in RNC2. And these are both, like, again, interesting and rich theorems. This is a long-running research program. It started with work of Cook in 1975, Sam Buss's thesis in 1986, and Kryazek has two like summary books about it. It is a logical path to NP versus co-NP, and it can make certain barrier results precise. So like Sasha Razborov, before the natural proofs paper, as far as I understand, was actually studying the provability of circuit lower bounds in these types of theories of bounded arithmetic. Again, I will leave the exact theories very vague, but you can read about them and they're wonderful. And yeah, this preceded the connection that Yen talked about in the talk just prior to mine, where the natural proofs barrier got started in trying to formalize circuit lower bounds in bounded arithmetic. So like, these are friendly theories that are nice to work with. They're part of a long-running research program on metamathematics in computation that's borne a lot of fruit, like the entire study of the natural proofs barrier. And let me give you a quick definition of VPV, the language of VPV. I'm going to give you function symbols for every function in polynomial time. I'm going to give you axioms for polynomially bounded induction. So you can do induction, but not too many steps of it to prove theorems. And I'm going to give you polynomially bounded quantifiers. So you can quantify over strings as long as those strings aren't like totally huge. Okay? And that's my cartoon 3-line picture of VPV, which we'll use for the rest of the talk. And again, you just want to think of super carefully formalizing a complexity theory textbook in the natural way, translations to logic. And the special property of these systems that we use and is used pervasively is witnessing. If you have an existence proof of an object in one of these bounded arithmetics, you can construct that object. You have an algorithm for it. It's inherently constructive. So here's an example. Let's say that VPV proves a theorem like for every x, there exists some y such that a polynomial time relation holds on x and y. Now note that if this was actually a statement in VPV, which it's going to be, right, because the theory proves it, those two variables are bounded, they're not huge, and that relation is a p-time function. It's expressible in p-time. What the witnessing theorem,
So I'm confused by the first V.
Oh,
different from PV, and is there any analogs so that it's conservative extension in bus hierarchy or not?
That's just the second.
Just basically take anything and hit it with RSU.
It's take anything and hit it with the RSU isomorphism. It's the second order version of the theory, where you have two sorts. One sort is numbers and one sort is strings.
What theory? S1?
No.
That's a question. So, what is the first order version of this theory?
It's Cook's PV, right?
So this is the second version of PV, but stated in the language of DIMACS.
But it's conservative over PV.
Yes,
Sigma 1
yes.
Sigma 1 formulas, yes, but beyond Sigma 1.
Which means that it is same as PV and same as S21. I can think about it this way. Yeah.
It's a little weaker than S.
It's like PV versus S1.
Yeah. They have a common conservative extension, which is conservative over all.
For this type of
them.
sentence.
Yeah.
Yes.
Okay, thank you.
Yes. So yeah, the PV stands for polynomially time verifiable, and the V in front of it stands for a. I'm working in a two-sorted extension, so I can conveniently represent numbers and strings separately. But that whole discussion was that presentation of the language doesn't matter for these results because those theories are conservative over each other. They prove the same thing under appropriate translations. Okay, so it's a lot like. It's almost like how the machine model doesn't matter in certain complexity classes, right? Like up to twiddling the way the taped heads and work stuff, it's the same. Thank you. I think that's an important point about bounded arithmetic as well. It is similarly robust to like the models of computation that we know and love. Okay, so witnessing. If I've got a proof of a theorem like this and there's an existential quantifier in that theorem, then there's a polynomial time Turing machine M that if you give me an x, right, where it says for all x, there has to be some y for which this relation holds, I can spit out such a y. And that's great. That means that you can turn a theorem that's originally just existential into a constructive statement about a Turing machine. And that's like the magic of bounded arithmetic. Okay. So let's start formalizing, right? What I'm going to formalize right here is the collapse of P to quadratic size circuits. And we can also talk about NP collapsing, but it's going to be easier to talk about P because I have symbols for every polynomial time function. Okay, so we're going to say that VPV, and the quotes are important, the quotes are semantic, proves that P has quadratic size circuits if for every f in P, every function in P, and for some constant greater than 0, VPV proves the following formal statement. Now notice I spelled out the English words for every f above, right? That's quantified in the meta language. What I'm saying is that for each polynomial time function, VPV proves the following formal state, which says for every n that's a number, there exists some c, that's a string, where the size of c interpreted as a circuit is quadratic, and then for every x, where, again, x is a string of length n, the circuit evaluated on x is equal to the function evaluated on x. And this is like a fairly picky textbook definition, but notice that every function in this, right, like even the size measurement on the circuit, if we like guess a string with our existential quantifier, that function, size of c, is a polynomial time function that can check if c encodes a valid circuit and if it does indeed have like the gate bound promised by the bound in this theorem. This is the point that I'm trying to make. Like circuit size, circuit evaluation, function evaluation for every function in FP, they all have function symbols in VPV1 by definition. So this is a legal statement in VPV1. And it's robust again, right? Like the choice of the algorithm, like which function symbol I use to represent each language in P doesn't matter. So yeah, and this is the remark that I made earlier. I'm quantifying each function outside the formalization in the meta language, in English, in the informal mathematics that we do around VPV. And yes?
Question. So this bullet in the lower left, what is the message that I'm supposed to get from that bullet?
The message that you're supposed to get from that bullet is that, let's say we have a language in P, right? We could represent that language by more than one algorithm, right? Like there could be more than one p-time algorithm for it. This sentence means the same thing, right? As long as I have this for every p-time function symbol, I can swap out the particular algorithm that I'm using inside the sentence. Does that make sense?
Yeah, I mean, I guess this will come up later. In other words, why you need that particular bullet. I'm trying to understand the significance of that bullet in this discussion.
So for our unprovability result, it's robust to the formalization, but I don't see why you need this right now.
Okay, yeah, I think actually that bullet might not be relevant for this talk. I just think this is a very nice property of the formalization of circuit lower bound. Sorry, that might be an unnecessary character.
It's
but
confusing.
yeah, yeah, and then so the two things that I really want you to take away from this slide is that when we assume VPV proves P collapses into quadratic size circuits, it's an infinite set of these statements inside the theory that's provable, and that note the quantifier structure. The quantifier structure is going to determine the shape of the witnessing theorem, okay? Because remember I said like witnessing theorems spit out what's existentially quantified. So what would be existentially quantified here? The circuit. And we will need a more complicated witnessing theorem from the previous slide, which only had two quantifiers. Okay. So that's formalizing a circuit upper bound in VPV. So what's our goal here, right? Like just to step back, now that we've actually introduced our theorems, introduced our theories, introduced all these things, what's our meta-mathematical goal? Well, we want to identify a natural theory, like VPV, that proves like all of complexity theory, right? Or so as much complexity as we possibly can be crammed into the theory, and it doesn't prove P equals NP. So again, like I said before, with the example of fixed polynomial size circuit lower bounds, this represents necessary progress towards P versus NP because true statements are going to be consistent with sound theories like we have. And inside the theory, P not equals NP would be true if it can't prove P equals NP. Okay? So that is one meta-mathematical goal, to show consistency to show consistency of a lower bound, you prove unprovability of the upper bound. And that's the kind of thing that we're doing. Okay, so there's substantial prior work on this. First, Cook and Kryjak in 2007 gave conditional unprovability of circuit upper bounds. Sontham and Williams, in seemingly unrelated work, but actually super related, gave lower bounds against uniform circuit classes. And then these three papers, Kryjak, Oliveira, Bezdovsky and Mueller, Bezdovsky, Kryjak, and Oliveira, gave unconditional unprovability of circuit upper bounds in various fragments of bounded arithmetic. How did they do it? They took this argument of Sontham and Williams and they pulled it into the formal theory in a very cool way. So they formalized those arguments to show that you can't prove certain circuit upper bounds in reasonable formal theories. Okay.
Wait,
Yeah?
can you say a little more about why the results of 2 would be relevant?
That is going to be the entire rest of the talk. There will be an actual picture, I promise. So, but yes, that's coming. Okay. Roughly speaking, though, right now, uniform circuits are circuits that you can print out with an algorithm, right? If I prove a circuit upper bound in existential statement in bounded arithmetic, I get a circuit printer from it, right? I get a circuit printer from it, right? In some weird form. So if I have a lower bound against uniform circuits and an existential proof in bounded arithmetic, these contradict each other. And I'll elaborate on that. So what are our results? We have new uniform circuit lower bounds paired with new unprovability results. So first, we unify, simplify, and extend nearly all of the previous results. So for example, for any fixed k, VPV does not prove P is contained in size n to the k. Also, for any fixed k, VAPC1, which is the theory that corresponds to BPP, also mentioned in Jan's talk, does not prove that ZPP with a constant number of queries to an NP oracle has fixed size circuits. And finally, this is kind of one of the most fun theorems in the paper. Efficient reasoning can't distinguish. This is really the takeaway message, right? Bounded arithmetics can't distinguish between non-uniform and uniform complexity bounds. In particular, VPV doesn't prove that both NP is not contained in P, so like a lower bound against SAT for polynomial time algorithms, and NP actually has poly-size circuits. So like this is possible, right? We could live in this world where there's efficient SAT solver circuits, but not algorithms. VPV can't prove it because it can't tell the difference. Okay, so how do we do this? We avoid reasoning inside the formal theories, basically, right? So we exploit the witnessing theorems to convert the existential quantifier in the statements of these upper bounds, these formalized upper bounds, take that existential quantifier, which is on top of a circuit, we turn it into uniform circuits, and then we prove exactly the right uniform circuit lower bounds to say, okay, circuits printed by this type of algorithm cannot exist. They can't do these problems. So basically, one half of the paper is executed inside of bounded arithmetic, formalizing this assumption, and the rest of the paper is executed just in complexity theory, proving elaborations of the Sontham and Williams circuit lower bound result. Okay. Yeah. So what do I mean by uniform circuits, right? Like what kinds of circuit upper bound, uniform circuit upper bounds are produced by proving existential theorems in bounded arithmetic? Oh, sorry, I'm going to mention open problems first. It would be great if we could show that P versus NP is independent of VPV. That would be amazing, right? And it's not even ridiculous to speculate that we might be able to do this at some point, right? Because recently, in a another great paper of Pick and Santhanam, they showed that VPV doesn't prove extremely strong circuit lower bounds, right? We show that VPV doesn't prove circuit upper bound. So if you squint and you pull these theorems together, maybe you could get some kind of independence. That would be nice. Yeah?
What are good examples of true things in complexity theory that we don't know how to prove in VPV? Meaning theorems, are there theorems in complexity?
Next versus ACC. I would say that that's my favorite example. Yan, is that fair?
I think that better example is like inversion of boundary functions. Like you know that every function has an inverse, but you can't prove it.
What's that again?
So this is like saying that for each y there exists x such that fx is y. This is inverse of the function. We are saying that there exists an inverse of the function f. For each x there exists y such that fy is x.
Okay, can I give another example? So AKS primality test algorithm, we don't know how to prove it's correct in this theory. We need like possibly stronger theories.
Yeah, but Jan's example is even unlikely. Like for one-way permutations, there exists an inverse, but it's hard to find, and VPV is not capable.
Yeah, so there's like three examples, right? There's Ryan's lower bound next versus ACC 0, and there might even be like an actual barrier to formalizing that in bounded arithmetic, because then we could if you got it into the right theory, we could turn it into a natural proof. And that seems difficult to get natural properties against ACC 0. The one-way function inversion, which is like a fundamental crypto primitive, and then correctness for AKS. Yeah. So there are examples.
The simplest example, if you could prove Formalization theorem, then you get algorithm for factoring.
Can you prove n-time hierarchy in VPV?
Can you prove the n-time hierarchy theorem in VPV? I don't know actually.
Yeah, I think Ryan's proof. I mean, he used PCP and n-time hierarchy and some stuff. You know how to do PCP, right? So if n-time hierarchy is also possible, I think it's doable.
I think let's take this offline. But when I was trying to formalize Ryan's proof in bounded arithmetic, the problem was the easy witness lemma and not the hierarchy parts of the easy witness lemma. Oh, let's talk about that then. Yeah, thank you. And then here's an easier open problem. Show that VAPC1, this theory that corresponds to BPP, doesn't prove ZPP is contained in size n to the k. And that would follow by improving our randomized learn uniform circuit lower bounds. Okay? Okay. So at this point, I know I'm way over time. Sorry about that. I can just like wrap up and say thank you, or oh, I'm not. 5 more? Yeah. No, I have like. Let's talk about the notion of uniformity that you get from the proofs in bounded arithmetic. Then I'll give a cartoon proof sketch. Okay. So here's uniform circuits. Here's a Turing machine. We give it as input n in unary. And as output, it gives us a circuit that computes a function that we care about on n bits. Very good. So here's deterministic learn uniformity with equivalence queries, which is what you get from bounded arithmetic. Here's an equivalence query oracle. You take a circuit, and you want to know, does it compute the function f on n bits? Shove it into the oracle, and it will either give you a mistake. It'll give you an input that witnesses that, nope, your circuit's wrong, sorry, try again. Or it'll say yes. And this is the formal version of the class, but basically, learn uniformity just says there is a deterministic polynomial time algorithm that makes a bounded number of these equivalence queries and prints a correct circuit for your function. And you can view the computation of this thing as, it makes an initial construction of the circuit, it asks an equivalence query, and it continues until it gets a completely right circuit. And it has to work for every valid response from the equivalence query oracle. Okay? That's the notion of uniformity that we get from bounded arithmetic. It's generally in this EQ model. Yeah, all of the leaves are correct F sub n circuits. And then the depth is the number of queries. Good. So here's the cartoon of our method for VPV in particular. We're going to directly transform uniform lower bounds into unprovability results. So let's assume that VPV proves P is contained in size n cubed, where that means exactly the formalism that I showed you earlier, that sequence of statements. So here's a VPV proof of the circuit upper bounds. We hit it with this KPT witnessing theorem, and we get a Turing machine that takes, 1 to the n input, makes equivalence queries. It makes a constant number of equivalence queries. And that's very important. That distinguishes this situation from, say, other learning settings, right? And then it prints out a correct circuit for the function f for every single circuit for every single problem in polynomial time. This is what would happen if VPV proved this theorem. Okay. So then we have a family of really technical contributions that extend Sonthan-Williams, essentially by having it the uniform circuit lower bounds of Sonthan-Williams, essentially by running them inductively on themselves. For every k, P does not. There are specific languages in P that don't have learn EQ1 uniform n to the k size circuits. So this machine can't exist. We know that KPT witnessing is true. So this proof can't exist. So that's where we get the unprovability from.
So I guess it's the constant exponent, like size n cubed or size n to the k, is determining this order 1 thing over when you do the learning? Or?
No. Actually, no.
Okay.
So that depends on the proof. So you don't know the proof.
Yeah.
What's that?
That depends on the proof itself. So
It's got a quantifiable nation.
I see.
Yeah.
So that's independent. The order 1 is independent of the exponent.
Yeah, the reason that the reason that the exponent is fixed there is because in the lower bounds on the complexity side, we can't get better than fixed size circuit lower
The k
bounds.
is related to 3. It's not the order 1, but the k that's related to it.
Yeah, it's this k over here in the uniform circuit lower bounds that's related to that. Okay.
Okay.
So yeah, so that's the unprovability of fixed size lower bound. So what if we didn't want to do this technical bit now, right? Like what if we wanted to prove something right now using only witnessing theorems, and we didn't want to extend Sonthan-Williams? Yeah, so thus VPV1 can't prove that P has cubic size circuits unconditionally. This is the theorem from before, right? VPV can't distinguish between NP is hard for polytime algorithms and easy for poly-size circuits. So we're going to assume these two things separately, right? And say we have appropriate formalisms for them. They look like the formalism that I showed earlier for circuit upper bounds. I'm not going to show those formalisms. The important thing about the formalisms is that they both have an existential quantifier, right? Formalizing NP is not contained in P in the language of VPV. You get an existential quantifier on a formula where the solver makes a mistake. Formalizing NP is contained in size poly, you get an existential quantifier on a circuit solving SAT, right? We're going to separately witness these formulas with two different witnessing theorems. If we witness this existential quantifier, we get a counterexample printer for purported SAT solvers, right? Like you give me an algorithm that tries to solve SAT, and my bounded arithmetic witnessing will give you a machine that prints out examples that thing must make mistakes on. If I witness this, I get that I can learn SAT circuits from counterexamples in a model similar to the equivalence query model that we saw earlier. This looks awfully suggestive, right? It turns out that if we combine these things, we get a contradiction, because I can plug my counterexample printer into the counterexample oracle of that learning algorithm and get rid of all the counterexample queries inductively. And then I've just got a polynomial time algorithm that prints SAT-solver circuits. But guess what? VPV proved that NP is not contained in P, so such a thing is impossible. So this is the dueling witnessing theorem part of the talk, and I thought this was just like kind of delightful. Yeah, and that's going to be it. Thank you so much.
Yeah, so getting back to my question from before about, so I asked what things can't be proved in VPV. I got 3 examples. Is there a natural extension of VPV that does all known complexity theory?
The AKS keyboard, can AKS be done in VAPC1?
It's not known how to do it in buses hierarchy.
Okay.
So not even known for APC2, right?
Not known.
Yeah, I don't think so. So I think the answer to your question is no, that we don't actually have.
ZFC.
Really? Okay.
It's an upper bound.
Yeah, probably.
Yeah. Well, just thank all the speakers again and the attendees for contributing to this.